In this video, we're going to talk about limits at infinity, which is also called the end behavior functions. Specifically, we're talking about rational functions. And rational functions have the form of some polynomial in the numerator over another polynomial in the denominator. The dot dot dots just mean that the polynomial can continue on. And because we're looking at end behavior, we only care about the highest degree polynomials. So in this case, we're pretending m and q are the highest degree polynomials in the numerator and in the denominator, respectively. What we care about is we want to know, is the numerator or does the denominator have a higher degree? So if the numerator is higher degree, then we say that this function is top-heavy. If the denominator is raised to a higher degree, then we say that the function is bottom-heavy. So the first question we want to address is, why is it okay just to kind of ignore all of these other polynomials? And what happens is when we're approaching infinity, we are concerned about growth. We talk a lot about growth rate, and we only care about the parts of the function that are growing the fastest, the parts of the function whose magnitude is increasing at the greatest rate. So if we think about this, say you had kind of an exaggeration, but x to the 100th versus x squared. As we approach infinity, this x to the 100 is getting bigger so much faster than this x squared that we can, in essence, ignore this x squared and just pay attention to this x to the 100th, and that will allow us to see what the function really does look like at infinity. All right, so now we have some understanding as why we can ignore the rest of the terms. Now we want to look at what happens with functions that are classified as top-heavy. So top-heavy functions have a greater power in the numerator than in the denominator. So say we have 7x to the 4th over 4x. This would be an example of a top-heavy function because x to the 4th is a greater degree than just x. One way we can look at this is we can divide. Our coefficients become insignificant when we have differing powers for the same reason that the rest of the polynomials become insignificant. When we're dealing with numbers close to infinity, the 7 really doesn't have much influence anymore. After dividing x to the 4th over x, we get x to the 3rd. So we say this entire function, as we approach infinity, will grow like x to the 3rd, and therefore will also approach infinity. For bottom-heavy functions, it's the opposite. Say we have 7x over 4x to the 6th. We again can ignore the coefficients and we look at the degrees. After we divide, we say that this function will grow like 1 over x to the 5th, which as we approach infinity is going to approach 0. Another way to look at these top and bottom heavy functions instead of dividing is just kind of to look at growth rate. So if we look at x to the 4th over x, once we pretend that we are plugging in really big numbers for x because x is approaching infinity. So say we plug in like 1,000 to the 4th over just 1,000. We see that this top is getting the magnitude of the numerator is increasing at a much greater rate than the magnitude of the denominator, and that's why we're approaching infinity. For these bottom-heavy functions, if you just plug in a really big number, say 10,000, and this would be over 10,000 to the 6th, we see that we have this huge number in the denominator and a relatively smaller number in the numerator. So this is looking like 1 over a really, really big number, which is going to approach 0. The final function we want to look at is when the degree in the numerator is the same as the degree in the denominator. So if we looked at the function 7x to the 6th over 4x to the 6th, the growth rate of the numerator is equal to the growth rate of the denominator. If we do our division trick, we get 7/4, which is going to be our horizontal asymptote. So as we approach infinity, since these functions are growing at the same rate, we're going to approach that horizontal asymptote, regardless of any other pieces we have in this polynomial. Because as these larger terms start to dominate, that vertical asymptote will be approached. All right, now we're going to go through some examples. The great thing about limits at infinity is once you kind of understand the rules, the examples go really quick. So if we look at the numerator and the denominator, we notice that their degrees are equal, so the powers would cancel out, and this is going to give us a limit of -5/2. We look at the second one. The numerator has a degree of 1. The denominator has a degree of 2. This function is going to grow like 1 over x. It is bottom heavy. We are approaching 0. We look at this function. We have a x squared in the denominator and x squared in the numerator. The growth rates are equal. Therefore, we look at coefficients, and we're approaching our horizontal asymptote of -3/2. In this function, our numerator has a growth rate of x cubed. Our denominator is growing like x. This is going to say that the function is growing like x squared. Our top-heavy function is approaching infinity. If we look at this function, we are remembering our limit properties, that the limit of x approaches infinity of 4x plus 3 over x squared is going to be the same as the limit as x approaches infinity of 4x plus the limit as x approaches infinity of 3 over x squared. We can now evaluate these individually. 4x is going to approach infinity. 3 over x squared is bottom heavy. That's getting 0. We have infinity plus 0, which is just going to approach infinity. Another way to think about this is if we look at the original function, pretend again that we're plugging in really, really big numbers. Say we plug in 10,000. We plug in 10,000, and this function is going to look like 40,000. We plug in 10,000 here, we're going to get 3 over 10 to the 4th squared. This part of the function, this is a super small number, almost 0. We see that this part is dominating. We're going to approach infinity. This is also a really good test of conceptually what's happening when we approach infinity. So let's just look at the numerator. Let's look at this numerator as z is approaching infinity. We see z squared plus 9 square root. As z gets larger and larger, z squared is also increasing. The magnitude's getting greater and greater. This 9 is becoming pretty insignificant. That means that this numerator just looks like the square root of z squared, which is going to look like z. When we look at the denominator over z plus 9, again, this 9 is becoming pretty insignificant. The denominator is just going to z. This leaves us with z over z. Since those are the same power, their coefficients are both 1, our limit is going to be 1.